right, here goes the YouTube, hopefully. It should be going. All right. Welcome, everyone. Welcome, YouTube. Welcome, everyone on Zoom. It is our next Water, Wetlands, and Watersheds seminar. I think we just have just a couple left. Yeah, you guys are all making it through the semester. And we have one of our very own Center for Coastal Solutions postdocs with us today. So we have Dr. Maureen Diaz. This is Bea or Beatrice. She's a postdoctoral researcher at UF here. She works with Dr. Andrew Altieri. She has her PhD in ecology and nature-based coastal protection from the Netherlands, like the whole country. I assume there's some sort of institution there, but she focuses on right now, especially seagrass restoration and trying to improve resilience. And actually, it's an interesting project. I think what you'll talk about today is looking at the resilience of some military installations, which are often at the coast and more and more facing threats from climate change and sea level rise and extremes, although we'll see how the next several years sort of fund research in that direction. This work is funded by the Department of Defense, as well as NOAA, the Restore program, the Coastal Restore program. And her research supports the planning, permitting, and design of future seagrass restoration. And a particular, I don't know, is it classified or? No? Yeah?
No, what's up?
No, at Tyndall Air Force Base. Okay, so, yeah.
Okay.
All right, so we'll go like this and you should get
Thank you for the introduction. So today we'll talk about feedbacks that can prevent seagrass colonization, and also from the aspect of passive seagrass restoration, which is when you don't actually put transplants of seagrass to recover a seagrass meadow. First of all, this work has been part of the East Bay Living Shoreline and Seagrass project funded by Bay County. And it's a collaboration between the Nature Conservancy, Jacobs Engineering, and the University of Florida. The goal of this project was to restore 5 acres of seagrass to increase the resilience of the base coast. And well, this is the coast, and the Air Force Base is like here. So they are trying to increase resilience more in a natural way. And one way is to restore seagrass. The role of the UF in this project has been to identify processes that are preventing seagrass to recolonize one area that they identified as possible restoration area, then inform the planting design, and also test passive restoration techniques to see if they work, and then restore. So as a general background, seagrasses are the only plants that make flowers and that can live in the marine environment. They are not like algae. They have, unlike algae, they have roots, rhizomes, and flowers. Seagrass were once algae, they evolved and converted into terrestrial plants, and then at some point in the evolution, this part of plants came back into the sea. So they evolved outside the terrestrial environment and then adapted again to the sea. For example, these are flowers of Calathea. Well, this seagrass that is more flat. And seagrass provide many ecosystem services that are very important, like coastal protection. They eliminate waves, they stabilize the sediment. They also provide grounds for fisheries, like the fish would lay eggs in the seagrass. Then they stay the first stage of egg right there, and they move. They of course enhance biodiversity. They also have cultural value. People like to swim there or scuba. They also store carbon, which is very important in the face of climate change, and improve water quality, and also control diseases just because they keep the environment more clean. However, they are declining everywhere due to a lot of different stressors. It's not just one cause for that. These stressors can go from increasing temperature, like if you have one seagrass meadow that is adapted to a specific temperature, and then in the summer you have a heat wave, then this seagrass may not survive. Sea level rise. This one is because seagrasses are adapted to a specific light condition. So if If sea level rises, these conditions can change, they will need to adapt. Fisheries, like trawling, this can destroy seagrass meadow, harvesting. Seagrasses, for example, used to be used also for like make carpets, but that was the dead leaves. Invasive species can also replace the seagrass, ocean acidification. Aquaculture can also be negative if the deposits go on top of seagrass meadow, dredging, shipping accidents like directly from the seagrass. Urbanization, including runoff. I guess you have these topics in your course. So the runoff at the end arrives to the sea, so this can also affect seagrass. And also one is desalination plants. And extreme weather events, like if we have more, for example, hurricanes, they could impact also seagrass meadows directly, like ripping up seagrass, or indirectly, like we found in another location that a hurricane changed the sediment dynamics of a beach, and then the seagrass started to disappear. So that's indirect, but. And the biggest problem here is that once the seagrass is gone, it's very hard to recover. And this is where this work starts making more sense. A well-studied example, because we still need to understand many things about the seagrasses, is the feedback of light availability. When you have seagrass attenuate waves and trap sediment. This creates an environment with more light availability needed for the seagrass survival. But when you lose the seagrass, this sediment is not stabilized anymore and can resuspend, creating low light availability. And also more resuspension can also make more nutrients available for phytoplanktons and create blooms, which also reduce the light. So all this can lead to the difficulty of recovery, of seagrass to recover. There are other feedbacks like sulfite. If you don't have seagrass and lucinics, which doesn't appear here, the sulfite concentration can increase and seagrass cannot tolerate it, so they cannot establish. But when they are there, they create these positive feedbacks that reduce sulfite, so they can live there. This is very general, but if you're interested in this paper, they explain all these feedbacks in more detail. The one we will focus today is bioturbation. Bioturbation is the rework of sediments by biotic components. In this case, here we have mega grazers, so big animals, including stingrays, whales, seals. So they basically are like moving the sediment. So if you used to have a meadow, the meadow disappears and these animals start digging around, they can prevent the recovery of seagrass. In our case, we studied this in San Andrew Bay in Florida. We zoom in a bit. This is the bay. The green polygons are seagrass areas, and this is the Tyndall Air Force Base, and this circle is our area. This area became bare in the past. We don't know exactly why, but it seems like a large sediment deposit. We couldn't figure out. The Air Force Base also think that maybe this is when it was being constructed and maybe there was some sediment. And the thing is that the meadow has been closing, but nowadays there are still these gaps. So these were the gaps that they identified as a possible area to restore. These gaps are surrounded by Thalassia, Paludule, and Rupia. Like all this darker area is seagrass. We discarded the option that these patches may be higher, and that's why there wasn't vegetation, because in shallower areas there is seagrass. So that was already like not an option. And all this is marsh. So it's cool because you have the seagrass really close to the marsh, and they even overlap in some areas. If we go in the water, what we found at the first day is that all the area was super bioturbated. So that was the first thing saying, hey, like something is going on here. And this was made by stingrays. This is a stingray laying on the grass. When they are in dense meadows, usually they don't dig. At least the ones that are small. There are bigger stingrays that may do some holes in the seagrass, but normally they dig here because there is food. They eat invertebrates. We found stingray pits that have uprooted rhizomes. This is a rhizome of a seagrass that has been pulled. And this is, well, with the slate, you can kind of see a bit the size. But we found pits of maybe 1 meter diameter, like I could fit inside the pit. So they can really create a lot of bioturbation. And these are holes of ghost shrimps that live in the ground. They are not the shrimps like the ones you can imagine swimming. These live in the ground. And the stingrays eat the shrimps. If we look in the dense seagrass, we didn't find ray pits for the shrimps. And this is used to show you the amount of stingray pits that you can even see from Google Maps. Like all these little dots are stingray pits. So the hypothesis that we thought that was happening here is that the sediment became bare. We don't know exactly why, but it was colonized by shrimps, which are eaten by stingrays, and the stingrays create these pits, so they prevent any seagrass from colonizing. And if there isn't seagrass, there are more shrimps because they prefer bare areas. So for this, to test this, we did 2 experiments. One was two experiments in the context of passive seagrass restoration. Now you will see why. We tried to exclude stingrays with bamboos, which are biodegradable, as a possible measure to restore the area by just putting bamboos, which will biodegrade, so that you don't need to remove them or to be worried that there is plastic or anything. And then we also measured the sediment dynamics in the area to see what was going on also with the sediment. So I will start with the stingray exclosures. We did 3 treatments. Well, one was the control, which we marked with 1 bamboo. Then we did a perimeter plot. This is like the top view. So there were bamboos in a 50 centimeters or 50 centimeters, doing like a perimeter. And then we did the same, but putting bamboos in a grid situation. And we also put a sedimentation plate in the middle to measure changes in the sediment level. And we repeated this in 2 patches. So there are 2 replicates of the experiment. These exclosures were installed. 1 set in the seagrass edge. So where the seagrass was finishing, we put bamboos to see if it could expand. And also 1 set in bare sediment to see if they could colonize in the middle of it. And this is how it looks in the field. This is a control. This is a perimeter on the seagrass edge. And this is a grid.
Hey, is there a bamboo right over in the corner there? It usually is. No, okay, that would be useful. Okay. It's almost, it was,
These bamboos are thin, like
yeah.
8 millimeters. They are thin like this and like this long.
It's actually in the chalk.
Oh, yeah, on the chalkboard. Yeah.
Okay.
Uh-huh. I brought that.
They were like
Uh-huh.
like half size of this one.
Half the height.
Yeah,
Yeah.
half. And we push them by hand in the ground. So they are very easy to install. As a response variable, because this seagrass has many shoots and it's very difficult to count all the little plants, we counted grid cells with seagrass. So we had this grid, it was a PVC with strings, and we counted how many cells had seagrass. Now going with the results. The exclosures excluded the stingrays, so we didn't find any pits within the exclosures, and floating fragments of seagrass established inside the exclosures. So initially, it seems that it works. Here we have some data. These are, the yellow are the controls without unboost, and the green and blue are the two treatments, perimeter and grid, for the versant and the seagrass edge. And we see that after 1 month, we have already new cells with seagrass. Then after 2 months, in September is when we saw most effect. Then in February, 7 months after, the effect was not as apparent in the seagrass edge because seagrass in winter dies off. But there was still some visible effect in the meadow, like in the versant. And then for the last measurements in July, in the middle of the versant, we still saw some shoots, but in the seagrass edge, there was a general retreat in the area because there was a mat of algae covering all the meadow in February, and it kind of died off in the spring, so it killed the seagrass. And I'm not sure if that's normal, but that year and the year after, that meadow has been not doing very well. But anyways, we also saw that these new recruits would not survive because they were being valued.
Because they were being.
Sorry,
Yeah.
boreal.
Mhm.
And to understand this other part of the story is where the sediment elevation changes enters. So we put these sedimentation plates with the sediment. These are squares of plexiglass, 10 by 10 centimeters, that you put below the sun. And there is a string with a float, so you can find the buds. And how it works is you insert a metal rod until you touch the plate, and you measure the distance from the plate to the surface of the sediment. So every time that you go to the field, you do that, and you get the difference of the sediment that is on top of the plate. And we install this in each plot and also in the inside the seagrass meadow. And in addition, we measure also RTK elevation, which is like a GPS that you measure the real elevation in the ground to compare the results. And we did that after 1 year, like before and after. The results of the sedimentation plates were very interesting because they show that there was sediment accretion, like constant sediment accretion. And that cannot be, because if in 1 year you have up to 20 centimeters of accretion, like you would have a month outside the water. So that was, something was going on here. So when we check the real elevation with the RTK, we could see that the plates were actually sinking because of the streams that I explained at the beginning. So those streams that the stingrays were eating, they bioturbate also and they excavate. And they can create a lot of sediment turnover. Which that, like this species in this area of the northern Gulf of Mexico, has, there isn't any study of them affecting seagrass. So this was kind of known for other areas, but not in here. So this species, Lepidophthalmus lucianensis, they create a lot of sediment turnover. So basically, imagine if we put a plate here and they are excavating below the plate, it kind of can sink. Here is the data. The gray boxes is the elevation change measured with the sedimentation plates. So it's showing for the controls, exclosures, and the grid that there was sediment accretion, but we know that it was sinking. The black boxes is what we measure with the RTK, so the actual change in elevation. And we see that there wasn't, like, these 5 centimeters can be error, but it was way lower than what the plates recorded. So the sediment was relatively stable. And also to prove that, the plates inside the meadow, they didn't sink at all, like didn't show any sediment accretion or anything. And as a last thing that we tried, we put seagrass mimics, which were a piece of cord attached in the ground, in the bamboo plots and also inside the meadow to see if they would get buried. We didn't try with real transplants because we needed a special permit that it takes like very long to get that. So we used mimics. And similarly to the plates, they were not buried inside the meadow, but the mimics that we put in the seagrass edge where there are shrimps and also in the versant where there are shrimps, they got buried. And this is, I'm not sure if it's easy to see, but this gap here with this dead seagrass, I did it with my hand moving the sediment. So if you were swimming, you would see this bare sand, and if you would move the sediment, you would see seagrass buried. So in conclusion, in this system that we studied, we find dense meadow areas with high density of seagrass, low cost of shrimps, and low density of preppets, less sediment turnover, and less seagrass burial. And on the other hand, we have these bare areas that doesn't have seagrass. Then the shrimps prefer this area because the shrimps avoid the seagrass because they cannot dig easily through the rhizomes and the roots. That's why they are more in the bare area. So if we have these bare areas with a lot of shrimps, the stingrays digging to eat the shrimps and other inverts that go here, and sediment burial, like seagrass burials. If we put bamboo exclosures to limit one of the parts of this feedback, because this feedback is not only about the stingrays now, it's also about the shrimps, we can facilitate the initial seagrass establishment because the stingrays are not tripping them off. But then after some time, we have the problem of the burial by the shrimps. And this burial is also happening in the seagrass edge. So even if the seagrass tries to grow, these shrimps here are like keeping it, preventing the expansion. So following up with the result, how to apply this for restoration. One option is if we don't know for sure what is the reason for this area to be bare, like in our case, we don't know for sure. One option is to leave this area as is, as a ground for stingrays and shrimps. Like habitats are mosaics most of the time. So having a bare area in a seagrass meadow may not be a bad thing. It may be just that it's an area that it's other organisms live in that. So it's not bad. But if we really know that like we are the reason of that gap, then to be able to restore this area, we first need to address the sediment turnover, and that's not easy. I have been reading about how to manage shrimps, and you can imagine it's not like there isn't a good answer because like we were thinking maybe on capping all the area with a like coconut fabric to prevent, but imagine just what is that to cover up like 5 acres of coconut fiber? It's just crazy. And there is another option of using like a chemical that kills the shrimps. But as you can see, also that's not the most easy or straightforward method also to use because it can affect other parts of the ecosystem. So there isn't an easy solution, but we have to take it into account. And if you want to restore an area and you see that there is this problem, probably the restoration will fail. So to save money, it's good to know. Yeah, so that's it. I would like to thank all the people that helped me in the field. And thank you for listening. This is a little seahorse that we found in the exclosures. What's like 1 centimeter.
Thanks, Bea. So questions from the room. I'll check on YouTube here. Yeah, Gina.
Did the work start after Hurricane Michael or was there?
After, yeah. But I didn't see any effect of hurricane Michael in the size of the areas.
Come in? No, come in? Yeah, Kathy.
Is it, of the three species of seagrasses, does one grow faster than the other and might it respond to a little bit of like fertilization?
Yeah,
Those areas?
the rupia was the one like was attaching faster,
Mhm.
and then halodule. And Thalassia, I found one shoe. That was surprising. I did not, Thalassia is the one that grows slower. Normally, if you would want to restore, you put first halodule that grows faster. And once everything is stabilized, try to add Thalassia. These are the latest theories for restoring. Yeah.
Perhaps fertilizing pellets or something that we
Oh,
should
fertilizer.
give them a boost.
Yeah, I don't know. Because the problem here is to exclude the stingrays, the rims, we will need like at least, I didn't show it here, but at least 50% cover of seagrass. So if the booster could bring the seagrass to grow to that level fast, yeah.
Yeah, I mean, one thing you consider, like, you don't want to cover the whole thing in coir, but you could pre-grow sort of like sod. Like, you know, you can take coir mats, like the thick blankets, and you can grow seagrass like in an off-site nursery or even.
Yeah.
like, maybe even like a nearby, like natural nursery that's protected more completely. And then you can transplant them almost like, you know.
That would be an
Patches.
option. Like you really need to transplant something thick that is
Yeah.
not going to.
When 100 years ago, working in New York City, we were trying to restore salt marsh in an area that had a lot of concrete had been dumped, and so the substrate was very hard and there were cracks, but like you couldn't plant spartina into it. So we planted in these thick coir mattresses and then allowed them to grow out in very dense roots and then placed those and they began to capture their own sediment.
Yeah,
And so I wonder if the whole thing, it still has the risk of sinking.
that's another
From
question to
existing
resolve,
shrimp burrows,
how big should be the patch to not be buried from the sides.
Yeah,
Because if you do like, maybe like this size, it's buried from the sides, but if it's,
but like the size of this table.
if it's
for
this
example.
table, maybe.
Yeah, but I mean, so you grow it and then you like roll it up and you put it on the boat and you take it out. Yeah.
Is it near an Air Force base or it's near well, whatever.
Yeah,
So I'm not, has there been any like dredging or any like large construction projects around the area? And if so, has that affected
this
how
is
how
what,
would influence like the sediment turnover?
dredging, not. Like, I'm sure in the past, yes. This is the area, and all this is marsh. So it's not like there is a construction right there or a canal that directly could bring sediment. That's why I was so sort of discarding that option. But, I mean, something happens. They will construct it, don't they? But
Yeah.
there is no.
Mark?
Do you have a feeling, I mean, you were doing some sort of density estimates, and I think you might have just alluded to it. Do you know where that change point is between kind of sufficient seagrass to prevent the shrimps from being a factor versus them? You're almost having two stable states, and any idea
Yeah.
where that change point
Is
starts to
around
occur?
50% seagrass is when you stop seeing the shrimps. And like you can see low densities, and when you have 70% seagrass, then it's like stable.
Good.
Yeah,
So is this a phenomenon, the sort of bear patch, shrimp, stingray pit part? It's like, you know, like the mud flat sort of corollary. So is that like a very typical part of the matrix and everywhere else you see these, they occur regionally, or is this like
Yeah.
a very odd thing?
I didn't include it here, but I monitored other patches like in this area. So there are more patches around That's why we also thought it maybe because of that and not a specific thing of this place being a dredging or something, because we found more patches that are bare, full of stingray pits and the fruits. But how they initially created, it's still like, could be hydrodynamics. Like there is this paper that proposed that if there is a disturbance by a stingray, for example, and there is a bit of seagrass ripped off, if there is a storm with waves, that hole can grow bigger.
Yeah.
So that may be a possibility.
Well, maybe a natural phenomenon,
Yeah,
like a gator hole.
Yeah, or like in the springs when you get like enough velocity and you rip up. So is there some way to do like a temporal analysis of the bare patch growing, shrinking, growing, shrinking?
Time series of
This
variables.
Is what you have.
it has been shrinking, but it would be cool to see now how it's doing after that algae die off. Because maybe now it's bigger, but I don't have new imagery available.
Questions for?
How much do you think your stakes influence the algal capture? I mean, you had it in the control as well, so it's kind of a blanket, but on the other hand, do you think there was a disproportionate influence because of your stakes?
I saw
Assuming it's stripped
algae,
algae, right? There wasn't
yeah,
epiphytic growth that was.
well, the algae that I'm talking about, it really attached to the seagrass.
Oh. so
Like it was not
epiphytic.
drifting, it was growing.
So it's a nutrient.
Yeah, so I'm not an expert on algae, but yeah, and that algae grew a bit on the bamboos also, but like everything was covered in algae. And drifting algae, the first year we saw some, but there wasn't a lot more than in the meadow. So it was kind of sparse. It was not, we were lucky, it was not really a big problem, I think, in this location. In another location, maybe, but no. And something I didn't mention, at the end, we changed the location, so we are not restoring this. And we moved to another place that is in more need of restoration.
Has the shrimp or no shrimp?
There are shrimps, there is erosion of sediment and turtles and manatees. So it's a whole set of different.
This wasn't hard enough, yeah. All right, well, let's give another round of applause to Dr. All right, and next week we have our own Calvin Kong is going to be presenting here on his work about mangrove encroachment on Florida's Gulf Coast. We'll see you then. Until then, enjoy beautiful weather. Get out to a wetland. See you later.